Okay, so welcome back. Our midterm is on Thursday, right? And today we're going to spend time reviewing the topics which we covered before the midterm, right? So hopefully to improve our understanding and just perform better on the midterm, right? So let me just start with this slideshow. So midterm will be open everything, but the internet search and explicit communication. So you can open your laptop, you can essentially like open any of the lectures, you can watch the videos, video recordings if it helps you. You can read the source code, you can you can type in the programs, you can use GDB. You can use any of those tools like readout and objdump. This is all allowed, but you cannot type a search query asking for a question. You cannot type in a chat or communicate in any other manner, and you cannot obviously like ask ChatGPT. Although it would be fun to experiment with that. We should do it one day. Any questions? And it will be in this room, a regular class time. It will last the same amount of time as the class, right? So, and it will be sized appropriately to essentially to make sure that you'll have enough time to solve the midterm. Question?
Do you know how many people will be here on Thursday? I'm just wondering if we'll get
squished.
2 desks per person.
We have around 90-something people in the class. So how many chairs in this room? I don't know. You can quickly count. I assume that everyone will be here or close to everyone, right?
Will this be on paper or is it going to be like a grade school?
I think we'll try to make it on paper, although it's very wasteful. I mean, which one is more convenient to you, for example? So Gradescope is more convenient. It's also more convenient for me, but it will be like free answers, so you will have to type and stuff. And I don't know what to do with pictures. So if I ask you to draw a diagram, then you can snap it with a phone and upload it. I don't mind it. So Gradescope is more convenient. It's way more convenient for me as well. I don't have to deal with paper. Okay, cool. Let's do then Gradescope. Everyone agrees, right? Okay, cool. Okay, thank you for suggesting this. Anything else? Any other questions? Yeah, sure. Yeah, whatever works. I mean, I would be happy to give you an extra time to snap pictures, but like some people will start showing up in this room, right? So we'll have like extra 5 minutes. Doesn't just try to be. Anything else? Good. So just again, you see these 2 pictures, right? Which one do you like more, or which one is better? The one on the left or the one on the right? The one on the right. So why? One is overexposed. So if we take a look at the histogram for these 2 pictures, right? So, which I took today in the morning. Let me quickly use my pen. So all we see, all the information is here on this overexposed picture. And on this picture, this is the median, right, roughly, I mean, by eye. And you have a lot of information, right? So you have some pixels which are here in the light zone and some here in the dark, somewhere over here, or even on the dog itself, right? And here, everything is bright, right? So this is kind of to show you the difference between an easy exam and an exam which is a little bit harder, right? So this one is easy, and everyone scores well. This one a little bit harder, so people score roughly here. Let's say maybe it's 80%, right? Median is around 80. So I tend to give exams which are closer to this picture. Just don't be offended by that. There is no goal to tell you, okay, look, you perform poorly. I just want to see the full histogram, like this one. I want to see the top people in the class, which are right here, which clearly know what they're doing, right? I want to show you that you can thrive to be in this, like, thrive to be towards past the median, right? Because the real world is a little bit harder than just a simple exam, right? But again, it will not affect your grade in any way. So, you know, it's obviously that this is an A, but don't you worry, like this one also will be A because of how we curve the class and do everything else, right? I tend to give a little bit more challenging exams. I just wanted to be upfront about it so people don't get scared or offended. Moreover, I mean, to be honest, I used to give even more interesting exams, but then I kind of backtracked a little. So they're just fine. So nothing super hard about them. And quizzes are kind of representative. And you said, okay, the last quizzes were a little bit harder than the first ones, right? So the first one were obvious, like I didn't have anything to ask. The last ones like show you what kind of problems you might want to solve, right? Okay, that's it. Let's go back to questions. So I prepared some, but I think it's more efficient to essentially just go through the questions which you guys want to hear. So quiz 6, please discuss question 4. Okay, let's go there. Any questions in the class? Let's give priority to the people who are here in person first. Right, that's the last topic which will be covered. So we're not going to cover boot because we didn't have a homework on boot, so it's a little bit abstract. And I even dropped the quiz on boot because just it will be better to do after the grade, right? So just it will be fresh in your memory, stuff like that. Anything else?
Is there any question we have to use GDB or compiler to finish it?
No, you can do everything by just thinking about it. But if you believe that GDB or a compiler might help you, you're welcome to use it. Because in real world,
It's not necessary.
It's not necessary. The way the questions will be phrased, oh man, now I have to somehow make sure that we delete this wonderful piece of video. Question 4, right? Okay, so it shows this. Solve the following paging headers translation. Assume the following context of the page table directory. Root of the page table, and these are the entries. Let me just, yeah, that's what I'm trying. And the following leaf tables at different addresses, right? Which physical address? Okay, so my TAs were phrasing the questions. Would you get after translating the virtual address 803001, right? So let me remind you how address translation works. So this is our address translation pipeline, right? So we always start with something what is called logical address, right? Remember that it has two parts. It has an offset, which is an actual number, which we use here, right? If we load something into the EAX register from the address pointed by the EBX, So this value of EBX is the offset, right? And there is also selector, which like something like data segment, code segment, stack segment, right? And those are, they slightly have a different format, but essentially we use it as an index into the global descriptor table, right? And the global descriptor table, which is part of the segment translation global descriptor table. Let me show you here. So essentially, you take these two parts, right? So segment selector, like it has some flag bits here, but essentially here we use it as a number. So this is, for example, 1. So we use this 1 to pick up the first entry from the global descriptor table, right? And this entry will contain two important pieces of information. It will contain some flags as well, but we can forget about them for a second. So it will contain base address, and it will contain a limit or the size, right? And essentially what we're doing here, we take this offset and we add the base to the offset, right? So this operation will be essentially here, it's addition, right? So you say, okay, whatever the number was here, maybe it was 0x0055, and the base was 0x1000, then addition will yield the following linear address, 0x1055, right? And so this linear address then goes as the input to the page table translation, right? To the paging. So segmentation ends here, and then we do paging, right? So what we do with this address is we say, look, we have this 0x1055, and we split it in 3 parts, which is 10 bits each, right? 10 bits, 10 bits, and 12 bits, right? And you say, look, what do we do with this address? So let's quickly, for example, we can use Python to do those translations, and we can go like this, 0x1055. This is the number. If we want to see the binary, we say like this. And you can split it by hand. So you say, look, I got it. This is the binary number, which I care about. And I know that the lowest part is 12 bits. So it's like this. Oh, sorry, I cannot even split. And this is the middle 10 bits. And apparently the top 10 bits are just zeros, right? So this is the top 10s. This is the middle. And this is the lower 12. Agree with this? So just no tricks. Like, okay, so we say, since the top part, this part is 0, right? We will choose entry 0 in the page table. Agree with this? How do we find the page table? There is a hardware register, which is called control register 3, which contains the physical address. So essentially, in physical memory, this is just where this root of the page table is located, right? So when we say, okay, well, we found this 0 here, right? This is entry 0. Do I have it? No, I don't. I wanted to show you the format. So what is contained here in this entry? 20 bits. What? What? Physical page number. So it's effectively the address of this one, right? So it's physical page number of the next, of the leaf of the page table, right? So this one. Agree? So let's imagine it's, again, like 0x7000, right? And this is exactly like this. This is where this page table is located in memory, right? So for this example, it doesn't matter because we say, look, okay, whatever, if we have information about this next entry, then it will be just fine. So we take the next 10 bits, right? And when we did the split, we said, okay, this is bit 1, right? And by the way, you don't have to do this. So you can do something like binary of this number, and you can, for example, shift it by like 10 plus 12, 22. It will, and what is that? How do I shift? Like this. This doesn't work. That should work. 0. Okay, so we shift it, and we shift by 12, you will get this 1, right? Of course, if you say, look, if there are some top bits as well, then we also want to mask, which is we want to select only the lowest 10 bits. So what is that? You can say, okay, I don't really care. Let's just type 10 zeros here, 10 ones here, right? And this one doesn't work either. Why? So this one works, right? It just, again, this is the way to quickly get this bit. So do you understand why I picked, why I put the mask here? Everyone understands or not? Because I shifted, and in case I would have something like 8000 right here, right? With the mask, it's still 1 because the middle 10 bits are still ones, right? And if I remove the mask, I will get something different, right? Agree with this? It's just that the mask allows me to select specifically this middle 10 bits because what I did, those are 10 bits. I shifted them, so result of my shift by 12, because this is 12, is that this 10 and this 10 are now at bits 0, right? But I still have those. So my mask, which is OX, I mean, I cannot write it in hex. Those 10 ones chooses this part, right? Clear? Okay. So, but again, if you don't trust yourself, you can just split it by hand. Okay, so we got 1. So we choose entry number 1, right, in this page table. And again, we pick this 20 bits, which is a physical page number. And it gives us the physical page, right? Right, the physical address of this physical page. The physical page number, essentially 20 bits, whatever this number is, let's say 0x10, okay, like 1000, right, for example. And so if this is a physical page number, then the physical, okay, just let's make it simpler. 0x50, did we use 55? 0x77, right? So these 20 bits are 0x77. So if you add another, if we add another 10 zeros here, 12 zeros, sorry, we'll get 77, 0x77 with those zeros, and the number will read like 0x7700, 0, I guess like this, right? So because page number 1, 0x1000, it's page number 1. So page number 77 is this page, right? I mean, this address. So the page number is this 111. Is that clear? So it's very mechanical. As long as you understand, you can always use this diagram to get this translation, right? So okay, let's take a look at what the question asks us. Okay, we say we have this physical address, right? Or you have the virtual address, this one. Okay, we do the same with this. Let me just we write it as a binary. Why not? We are lazy. We don't know how to use shifts and stuff, but we know how to split. So we split in 12. Here we take 5 and 5, right? So it seems to be relatively easy, right? So let's just do it again, just to make sure that let's do it differently. Let's do it with this masks. So we say, look, I first shifted by, what's the number? By how much I want to shift to get the first entry? Tell me. 22? Yeah, correct. So entry number 2, right? So we go backward here, and we say in the root of the page table, this is the root, right? Entry number 2 is exactly this, right? Agree? Okay, so since, remember, let me just start another whiteboard. So the entry itself contains 20 bits of physical page number, and the rest are the flags, right? So obviously we don't need the flags, right? We say, okay, forget about them, right? We don't care about them. So you say, sure, let's take this number And again, it's 20 bits of flags, so we shift by 12, right? And we get the physical page number 657, right? Which is in hex, if we want to do it, 0x291, right? We don't, because look, let me, maybe it wasn't clear. So this is the entry in the root of the page table, right? So we said this is the page table itself, right? So it has some entries. This is entry number 2, right? This is pointed by the control register 3, right? CR3, agree? And this top 20 bits are the physical page number. Okay, so what do we get? 2190, right? So, and as I said, like if we multiply this by 4096, we will get the actual address, right? Which is the address. So, okay, the leaf is located at this address, at this physical address, agree? Do we have information about this physical address? Let's take a look here. So it says, okay, wow, luckily there is something about it, right? So this is the at address, those are the entries, right? This is where the leaf is. So essentially what we did, we said, look, this number was 291, or x291, right? This is the physical page number. So we will use it as a pointer. So we will multiply OX291 by the size of the page table, 496, which will give us in hex this address, 29100, right? Agree? And this is exactly where the leaf of the page table is located, right? Right? So which entry we have to pick in this leaf? How do we go about it? Who can tell me? Next 10 bits. Okay, so here we get to this address, right? So we shifted it by 22. We got 2. We shifted by 12, right? And we need to apply the mask, right? Because we only care if we don't apply the mask. This is what we get, but this is wrong, right? So we say, okay, we apply the mask with 10 ones, right? And we get exactly, we get this number, which is 3, right? 1, 1 is 3. Agree with this? So we pick entry number 3. So do we have information about it? Yes, we do. So this is entry number 3. So this is it, 51C00B. Again, we say, okay, this is the physical address, right? No, this is the entry, but we don't care about the top. We don't care about the top. The bottom 12 bits, right? Because we say it's just flags, right? So we say, okay, this will be our physical page number of a page we're looking at, right? And we say, look, we already know how to translate it back into the page. We just add like 3 zeros here, right? And however, we have an offset within a page. So what is the offset within a page in this example? The last 12 bits. So what are those last 12 bits? And how do we even can identify them? Let me just save this one, huh? How do we go about the last 12 bits? Yeah, we just mask with 2 more ones here and be happy about it. It happens to be 1, right? So you can also see it here. This is this 1, right? Okay, cool. So we add this address with 1 because this is the physical address of a page and this is the offset within a page. So our solution should be then this last 1, right? Which is the address, right? So let's take a look what we say here. 1C, so kind of hit the correct answer. Any questions about how it was done? Okay, so what was the, I understand that if someone asks you to do that for the first time, you might get confused, and maybe there should be some, we should have some warm-up. So I've shown some examples in my lectures, right? So but the addresses were split already, so maybe it wasn't as easy. But okay, the quiz is a quiz. The goal of the quiz is just to prepare you for the midterm. That's why the quizzes weight so little. You can fail all the quizzes, you'll still be okay, right? But no one will fail all the quizzes. But okay, any questions?
Also, is there any chance that we can get the quiz answers revealed on the quiz to see who are they?
This is what I was trying to actually do over the weekend, and my TAs, they say that they see the answers, but can you show me? Can you send me a picture for how to do this, or for what you see?
Select the question you want to know the answer for, and then it'll appear. You don't have the question actually selected.
As a student, you have to click it to see. It only shows one at a time.
Okay, it shows one at a time, so then it works. And I created the test student for myself, but it was hard for me to experiment because I have to submit, and all the deadlines have passed, right? Have passed. So I wasn't able to submit anything, and then I stopped. But okay, so it's clear. So in order to see the answer, you have to click them one by one, right? Okay, cool. Any other questions? Good. Address translations. Address translation, we good, right? Okay. Let's go to the next one. Sorry. So I would prefer to first start with quizzes because those are the ones which are the most. Quiz 5, question 1. Okay, let's take a look. Quiz 5, question 1. Oh, really? That's how Gradescope works. Quiz 5. Can I somehow do it without showing you? Just unplug for a second because I cannot really show who got what grades. Okay, that's not bad. Yeah, that's what I wanted to actually cover as well. So this is a good one. So relocation. So that's another. This is where I suggest if you don't understand well how it works, right? So then it makes sense to kind of use GDB or type it in and see what's going on, right? So okay, let's go. Essentially, the question here is the following: in the code below, which lines, when translated to machine code, will need relocation? Right, so we have 32-bit and 32-bit code and no position independent code support, right? So let's take a look. We're not gonna look at specific questions. We kind of understand the shape, right? But let's go line by line. So what about line 2? Will it need a relocation, or like lines 2 and 3? So who think we need a relocation here? You think?
I think the variables will be relocated somewhere else, but I don't believe relocation happens.
Right. So those are declarations. I agree. So what does it mean in terms of a compiler? In terms of a compiler, there will be no even machine code generated for those variables, right? So those will be just constants. They will be sitting in a data section, right? And the data section will contain just 2 values, 8 and 5. So those 2 will be okay. No relocations, just data section. Agree? Is that clear to everyone? Or because some people said, okay, we'll probably need relocation here. I just wanted to make sure that we know that we don't.
But when I was with it, because I was confused at first, I'm like, relocation, well, we're going to move. The data section is going to be moved. It's code composition. So the data section moves, but the variable will be relocated, and needing relocation would seem very...
Yeah, I agree. I should ask it more explicitly. Again, like those quizzes were created by my TAs previous version. And I mean, it was a great exercise for them, and they had a lot of fun. But I agree that it's a little obscure in this specific case, in this specific 2 lines. But let's just make sure that we understand it. And I mean, you can argue back to me and I will say, okay, yeah, I did it for this instruction pointer points to the next or the current instruction, right? So despite the fact I think that the question was worded correctly, it just kind of, it's so nuanced to say, is it current or the next instruction? You really need to understand the pipeline and stuff like that. And so I give everyone just one. So I just change the rubric to make sure that no one loses any whatever points on that, right? But still, I ask you to kind of understand what is really instruction pointer points to. It actually points to the current instruction, and only move to the next instruction when the current instruction is parsed by the CPU. CPU understands maybe it's a move, maybe it's a jump, and if it's a jump, the instruction pointer increments not just by 4 bytes, for example, if it's the size of a move instruction, but increments by whatever the relative jump is, for example, or an absolute jump, right? So you can always argue that, and I will try to give you some number of points back. But nevertheless, you know, it's nice to understand as well. We had another question, right?
Yeah. So these two integers are saved in the data section, just not translated to machine code.
Correct. The compiler will not even generate a code to initialize them. It will just say, okay, look, like, let's put 8 and 5 in a data section. And every instruction which refers to 8 and 5, those instructions will have to be relocated, right? So we'll need to be like the addresses, the instructions which use those addresses will have to be patched by the linker or whatever, whichever part does the relocation. Okay, so I actually skipped some lines. So line 2, line 3, line 5, right? So because it's a little bit, line 5, so what is here? Say again? Yeah, so it doesn't even generate an instruction or anything. There is no instruction. It doesn't generate anything in the data section. It will generate something in the external symbols. I mean, it gives the compiler the signature of this, and maybe it will trigger. It will actually generate a symbol in the undefined symbols section, right? But I didn't want to cover that in too many details. Again, just make sure that you understand at least the high-level shape of it, right? And then when the program gets linked, you know, that symbol has to be found, right? Okay, so, and you know, what about this one, like lines 6 through 8? Okay, like to be more specific, line 7. Relocation or? We don't need. Does anyone think we need relocation here? No one. Okay, can you explain why we don't need relocation? Correct. They are passed as arguments to the function. And remember the calling convention, it tells you that the arguments are passed on a stack. So it's relative to the ESP or EBP register. So we don't need to relocate anything, right? Agree? Okay, and return itself returns, there's a little bit more about here. So return itself puts the return value into the register, right? So no relocation either. Good, so I asked about line 5. I skipped actually 7, so line 13. Okay, so what about this one? We don't need. Why? C is also on a stack because it's a local variable here, right? So it's declared as a local variable. We don't really know. Compilers are so smart that they might not even allocate it on a stack. They might allocate it in the register, but nevertheless, no relocation, right? Okay, what about this line, 14? We need, because we access a global variable A. So whatever we have, there will be a move instruction, right, which accesses A. And since A is in the data section, when we move the data section, this address will change, right? Agree? Okay, so what else? 13, 14, 15, 16. 16. What about here? Yes, no? No? Okay, can you explain?
C is a local variable, so the stack will work with the passing variable. And,
Correct. And red is a local variable. There is a little bit of a wrinkle here. Let me show you. What about this line? Say again? Yeah, that's exactly what I wanted to ask. So the difference between these two lines, despite the fact that both of them use only local variables, red and C and B. Oh man, B is global, sorry. There's also the function name. So for the add, since add is local function and it's declared as static, just to confirm that it's completely local, right? The compiler will generate a relative call instruction. So it will just jump backwards in the code, right? So no relocation will be required. However, for this sub function, since it's extern function, so the sub, we don't really know where it is, right? So this call instruction will be generated with zeros originally, or something like a loop which jumps either back to the program or back to the same instruction, so you don't crash in some funky manner, right? But this address of sub will need to be relocated, right? And also the address of B will have to be relocated, because when we push this B on the stack, we access the address of B, right, which is in the data section. Is that clear? Any questions? That's a little subtle here, right? I agree. So it's easy to miss.
Let's suppose we define add method without stacking. So in that case, we'll also use relative.
I think so, but it gets a little bit into the woods. And sometimes I think it will, yeah, I think it will still use the.
But when I see the L file in medial and so static method is need a relocation.
It needs a relocation. I think so too. That's why, and I don't really know the reason why. There is some logic about it, and I don't know. I don't know the logic. That's why I put static here. That's a great question. So if you dig up and you ping me on Piazza, I will dig up why it's done. My guess is that you actually can overload this symbol. So if it's not static, I think you can substitute add. No, I don't really know, but there is a little bit. So Kanchen, you know.
So I know it's something that if like you have already known the global variable, the first time the global variable appears, you need to relocate. But later it still appears as an R value, then we don't need to relocate it because it's already in register. But if it appears as an L value, then we still need to relocate.
What you're saying is maybe this B is actually in some kind of a register already, and then when you will pass it here, you don't even, it will not even, the code itself will not even touch the global address of B.
Yeah, I actually did some.
Yeah. No, I agree. That's also possible, and it's a valid explanation. If you tell me, okay, I think that compiler might generate this code, will not relocate B because B is already in the register because it was referenced 2 lines above. Yeah, that's a perfect answer. Even better than what I was asking for. Yeah. No, it gets a little like it gets a little unusual, right? So that's why there is also always room, because it's super concrete, and you say like, yeah, compilers work this way, but at least let's understand the general shape. So what about this line? Printf. Printf, yeah, that's an external function, so we'll have to relocate the address of it, and or at least figure it out. And what else? The string, right? The string is in the global section. Essentially, it's somewhere in the data section, and we use an address of the string, right? Okay, good. Any other questions about it, about this example?
For lines 2 and 3, what would happen if there was another value included in the head? Int A equals 5 and int B equals 8. Or like this different. I guess it'd be redefinition.
So what you're saying is that what you're getting to is that what if those initialization cannot be computed statically, essentially? I don't know if C allows it. Definitely C++ allows it, remember. So you have dynamic constructors, which is, I think it's a flow in a language, but whatever, they designed it this way. Remember what happens. So there's this init section, and this constructor is placed into that init section. And you can tell me, okay, I get it. So, and maybe C can do the same. So I don't really know. But you can argue and say, look, it might be in this init section, and the code will be running, and if the code will be running, it will need a relocation. Right? Okay, good. Okay, this is, I agree, so, but fun, and you know, like, the hope is that people who will get into this will be able to pass the most challenging interviews, job interviews, and will essentially get us at least something back in terms of salary later on in life. Okay, what else we have here? So no quizzes, and I think those were the two most complicated. The other hard, like, okay, I wanted to. There is this example which I have in my lecture deck. Let me show you. Is it really how it looks? Why? Let me just slideshow from current. Oh, sorry. Current. Okay, we can. I wanted to show you this question, so which is similar to what I was asking in a quiz. I was asking this in a previous versions of the midterm. So essentially, here we say, consider the following 32-bit x86 page table setup. So CR3 holds this address, right? So it's you immediately say that the lowest 3 zeros in hex is just those 12 bits which are offset within the page, right? So that's physical page number 1, right? But I tell you here, the page table directory, so CR3 points to this, right? So obviously the page, oops, sorry. So the page table directory is at this physical address, and it has these entries, right? Entry 0, physical page number 2, then entry 13, then entry 2, right? So it's this page is double mapped. The flags are present, user accessible and writable. So I usually don't play tricks with the flags, so I'm not gonna delete like present, just to kind of trick you into the case when this entry is not present, right? And there is this information that the entry, like physical page number 2, so obviously leads us to this location, right? So it has entries 0 and 1, and entry number 3 has entries 3 and 0. Sorry, so this is the physical address of this leaf, right? And so you have entries 0 and 1, which have this physical page number 5 and 5, right? So it defines a page table, right? So if I quickly draw it for you, so to make sure that we understand, so there is this root. Just maybe it's easier to context switch between these two. So the root sits at page number 1, right? And it has 3 entries which point us to pages 2, 3, and 2, and everything else is zeros, right? Then we say like, what's inside 2? Inside 2, so this pointer, there is a leaf, and inside this one also points here, by the way, right? And this 3 points to another leaf over here. And so inside 2 we have 2 entries 5 and 6, 5 and 6, right? And inside this one 3 we have entries 5 and 5, right? 5 and 5. Right? Agree with this? That's the drawing of what was, the graphical drawing of what was presented there. And this is at physical page number 2, and this is at physical page number 3, right? Any questions about this? How I drew it? Okay, let's take a look at what the question is. List all virtual addresses that map to physical address. And what? List all virtual addresses that map to physical address 5555. Even I'm confused at first. You say like, well, we have multiple virtual addresses that map to physical address. For a second, it throws you off, right? But remember, that's exactly the purpose of the page table. So if this is your virtual address space, virtual, right? And if you have physical pages, remember how we said, okay, multiple virtual pages can map to this one, right? That's totally normal, right? So, and this physical one is OX5555, right? Agree? So, which physical page number is this physical address? Huh? 0x5, right? So physical page number of this address is 0x5 because this 3 5s is just an offset within the page. And now what do we have to do? Like, which virtual addresses will map to this physical page number? How do we go about it?
We can find an entry in the leaf level. We can find out which physical page number.
I think you're right, but maybe someone else can tell me how to do this as well. So like, how do virtual addresses work? Imagine this is the virtual address V1, and this is V0, right? Or V2. So we say, look, if we take virtual address, let's make it blue, for example. We say there will be 10 bits, and an offset, right? 5, whatever, offset, 12 bits, right? We know that the offset should always be 5, 5, 5 in hex, right? Because that's an offset within the page. And now we say we need to find all possible combinations of these two, which land us on this physical page number. And we see where this physical page number is. It's right here in 3 different places, right? So just we have to find all the paths, essentially, which lead us to this. So this is one path. So it has to have 2 in the first, it has to be, hold on. It needs to have 0 in the top 10 bits, right? Agree? To choose entry number 0 in this page table. And it needs to have 0 in the second 10 bits, right? So this is the address. So it will be OX00555, right? Agree? Because when we'll be translating this virtual address, we will go through this check mark here and check mark here, right? Agree? Okay, we say, what else? Where are those 5s? So if we choose entry number 1 here, so this one has to be 1. And we can go through this, right? So it leads us to this one. And here we can have 0 or 1, right? Agree? So then we have to be 0, 5, 5, 5, or 1 and 1, 5, 5, 5, right? Agree with this? So of course you say, look, this is a little funky because this really has to expand, right? So if you care to expand those addresses, so we really need to write them correctly, right? But at least we got the logic, right? Any questions about it? So do we have an answer here? Let's quickly check. Maybe we don't have it. Okay. No, they found 4. So this one, and this one. So which one did we miss? Page 2, right? Correct. So this one, sorry. So another pass which leads us to where we want is this pass, entry number 2 here, and number 0 here again, right? So it will be the address which is which will have. I don't have space here. Okay, let me. So it will have 2 here, right? Because we want to land here, and 0 here, and 5, 5, 5 here, right? And if you say, okay, I got it. I got this logic, but how do I convert it to a real address? So how will we go about it? Python, exactly. So what we're going to do is we say, look, this address 20555 is like 2 shifted by 20, shifted by what, 22, right? Plus, what is this? 0 plus OX555. If we want to hex out of it, we'll do something like this, right? So supposedly, oh man, what did I do wrong? So it's 2. Say again. Oh, like this, right? No, this is the same. Should have this. No, mine. So unusual. So this is the address, right? How did you know? I don't know enough of Python apparently.
Yes.
Yeah, no, I get it, but it's ballsy. So this is the address which we got here, right? Precedence of readers is confusing here. Okay, what else? Let me just quickly see what else do I have here. And this was like kind of a little bit of a tricky question, right? So, but if you already seen one before, I tend to ask, okay, let's go back to the, maybe I'm pretty sure that you guys will land me on the same questions here. Fall 2020, 313242. Yeah, let's go with fall 2018. Okay, let's go in the order who, where are we here? So by the way, all the exams are publicly available, right? So where is it? Examples from previous years. So we go fall, what fall? Fall 19, 2019, 2018 actually we go. And where is it? 18 to A. Oh, that's the same. Oh, cool. Yeah, good job. 6A. So 6A, we didn't cover system calls yet, so those questions will not be on the midterm, obviously, right? So the cutoff is such that we only cover what we had in class 7. Obviously not on the midterm. 8A. Not on the midterm, just because we didn't cover it yet, because midterm was shifted was later in class. 2019 1B. Okay, let's take a look. B. Oh, this is a good one. Yeah, I was looking for this one. So this question asks you to understand the layout of the stack, right? So what happens here is the following, right? So there is this source code and the assembly of a simple C program, right? So which, we all understand. The CPU is about to execute the push instruction at line 12, right? So this is where the instruction pointer is pointing to, right? This one. Draw the stack and how it changes with every instruction of this program until foo returns. Lines 12, 13, 1 through 8, right? So, okay, this is probably relatively easy, but let's do it. So let's take a snapshot here. So this is Slack. Never turn on Slack. Otherwise, we'll never finish. This is Skype. And what's going on? Which one is my, oh, this one. Sorry. Let's take it here and we'll place it somewhere. So we have it in front of our eyes. Okay, let's start drawing the stack. So imagine there is something on a stack, right? Imagine there is a stack pointer, ESP, right? Points here. So this is address 0, so the stack will be growing downwards, right? So when we do this push, right? This OX1 shows up on a stack. This corresponds to this pushing this 1 as an argument to a function, right? So an instruction pointer will be pointing now here, right? So when we do a call foo, right, the return address, let's assume this address is 16, will be pushed on a stack, right? So OXF, right? Agree? So on the ESP will be pointing here. So now we are here executing this line. We're pushing EBP, right? So, okay, sure, let's, wherever EBP was pointing to, we pushed it on a stack. We move EBP, it's into assembly, right? So I should be explicit, but you can guess from those brackets. So we moved ESP into EBP, right? That's okay, nothing changes on the stack, right? So now we add the value on the stack, which is EBP. So EBP will be also pointing right now here, right? So EBP plus 4 is this, EBP plus 8 is this one, right? So EBP plus 8, we add 1 to it. So essentially we passed 1 and we added another one here, right? So this becomes 2. We move this one because we didn't use optimizations into the EAX register. Fine, we're ready to return. We're popping EBP. So at this line, essentially ESP, you can write it like ESP at line 7, for example, points here. When we returned, right, so this gets popped from a stack as well. ESP will be pointing here to this line, right? And I guess you can draw it to me as a sequence of diagrams, or you can draw it to me as like if it's online, you can just copy paste, use ASCII art to quickly just make a drawing. Question? Hold on, I didn't hear you. Sorry.
Why was OX at where it?
Yeah, so I mean, because this 16, like I can either write 16. Oh, sorry, I can write 16 or 16. Oh man, 16. Yeah, you're right, man. 16 is 1 0, right? Yeah, sorry. Any other questions? So this is relatively simple, so nothing really tricky is going on. But I guess the real question is, which was asked on Piazza, is 2B, right? Okay, let's take a look at 2B. Where is it? Oh no, it's not 2B. 1B. Okay, what is there in 1B, right? Imagine your CPU is identical to x86, but does not have call and read instructions. How will you implement the assembly code above? The code needs to support recursive invocation of functions. So any ideas? Yeah, exactly. So if you don't have, if you don't have call and return instructions, so how can you represent the call instruction or make it up out of other instructions? Who can tell me? Say again? So you say it will be a push of a return address, right? And then what? And then a jump. And then the jump to a label. That's correct, because this is exactly what call is doing. And some instruction sets, like for example, MIPS or ARM, they don't have a call instruction. They just have these two instructions. So, but what is this return address? So it would be cool to write it something like a push of the EAP plus size of a call, and you can say, look, you can be explicit about it, and you say, look, my call instruction is of size 16 minus 11, 5, right? So you can say, okay, let's push something like this on a stack in this specific example, right? Or the call on x86 can be of different size, right? And what about return? Do we understand why it will support recursive invocation because it does exactly what the call does. What about return? Yeah, we can just pop to EAP. And then what? You say just hop to EAP. Yeah, that works as well. It's a little unusual, or alternatively, you can write it. That's a funky instruction, but yeah, clever, should work probably. Alternatively, you can do something like pop into some register which is typically unused. And what is it? You need maybe some special register here. You say because you cannot overwrite EAX, and other registers are also kind of taken, right? So you can maybe say something, I don't know, pop into ECX, or ideally, and then jump to ECX, right? But then you say my calling convention should change, and ECX should be, what is it, a caller saved register, caller wants it, right? Because caller doesn't care about this point, right? But actually, you can take any caller saved register here, put already existing caller saved register. Okay, so a little bit like stresses your imagination, and some people were close to answer, right? Any questions about it? Yeah.
So something about being 64 question.
Okay, let's take a look.
Yes, that.
No, it doesn't. It just identical to x86.
Okay. Right.
Okay, cool. Okay, thank you for this. So to be, okay, let's take a look at to be. What is to be? No, this we already covered, right? To be. Okay, no, that's a little different. So here we say, like, it's just a simpler version of the same question, but it asks which physical address is accessed by the following move instruction, right? Here's EBX register contains this one, and just don't forget the segmentation is on, right? So I just make it simpler for you, and I say the data segment is configured to have the base of this, right? I should probably say that the limit is 4 gigs or something. So essentially, you take the value in EBX plus 8, and then you add the base. And at this point, you start the translation, and you have the page table, right? And from there, you go similar to how we did it before, right? Agree? Any questions about this one? Okay, good. Let's take a look at 2B. Draw a page table. You can use a format similar to the one above that maps virtual, or if you want to be more specific, linear addresses, 2 gigabytes to, like, this is the range from 2 gigabytes to 2 gigabytes plus 16 kilobytes. So it's just 4 entries, 4 pages, right? So four virtual pages to physical addresses from 0 to 16 kilobytes, right? So how do we go about it? So let's take a snapshot. It's also relatively easy, or like, if not just easy, but again, if you do it for the very first time in your life, it again can be somewhat confusing. So we'll put it here. So okay, it says, okay, we imagine this is our virtual memory, right? It starts at 0, goes to 4 gigabytes, right? It says addresses 2 gigabytes, right? So this is the specific address to 2 gigabytes plus 16. So we know that each page is 4 kilobytes, right? So if we want to do 16, we do 4 of this, right? So it will be addresses, literally the addresses which we will want to map are 0x8000 and 4 zeros here. That's page number 1. Page number 2 is 0x80001000. That's this page. Number 2. Page number 3, which we want to map, is x80002000, and page 4 is 0x80003000, right? Agree with this? Yeah, you're right. So in this question, I should probably specify that we are using 4 kilobyte pages. If you are super clever, you can say, look, I will use a 4 megabyte page, but then I can counter argue and say, look, then you will not be able to just map those addresses. You will map 4 megabytes, right? But I mean, I'm not the greatest person to ask the questions absolutely correctly, but I will be here in class, and you can always ask me a question, and I will clarify this.
Two things. First off, should we add page directory? Second off, aren't the page number zero index? Index start at 0.
Like you lost me a little bit. Wait. We want to map this 4 pages. It's the page table which maps only 4 pages. I just wrote down the addresses of those pages to simplify. Now we have to construct the page table, right? I can tell you where we want to map them. We want to map them at addresses 0 to 16 kilobytes. So if this is our physical, this will be these 4 pages, literally. Physical page number 0, 1, 2, and 3, right? And nothing else is mapped. We had a question.
There's supposed to be 2 zeros between the 8 and the page numbers, right?
You think that I didn't write the address correctly? So OX100 is exactly 1 page. And then this is the page number 2, number 3, and this is number 4, which is 16 kilobytes.
Sorry, the distance between the 8s and 3. I think you have 3 zeros in front of it. Or at least the problem key itself doesn't understand.
You mean these 3?
Yeah.
Oh man, then this is wrong. Sorry. Yeah, so there must be another 0 here. Like if you, again, good job, like good eyes. This is the address, and this is exactly 4 gigabytes, or 2 gigabytes, right? So, and the reason I know is that if you write it in binary, it will be just like 1 here, right? 1, because you kind of like split the address space in 2 gigabytes regions, and you say there was region 0, and now it's region 1. Okay, good. Okay, so now how do we go about constructing the page table? We say, well, we need a root, right? Definitely page table directory. And you say, it can be anywhere. It doesn't tell you where to put it. You can put it in like, you can even put it here, why not? Well, like you can put it anywhere, like you can put it here either as well. So you say CR3, for example, points to X0, why not? So this is the page table directory, sits in this physical page, right? Why not? And you say, since I want to map those addresses, right? How do we go about it? So which entry we need to pick here in this page table directory? Let's split then this one into 10, 10, and 12, right? So 10, 10, and 12, right? We can play the same trick which I was playing before. So we say, what are the topmost bits? So 22 happens to be 512, right? So this entry which we pick here is 512, right? And then we say, look, we need a leaf, obviously, for translation to work, right? We say, what? Let's pick anything. Let's pick 1, for example. Why not? We'll put 1 here. There is not a single solution here. There are multiple solutions. You like any of them is valid. Like physical page number 1, right? And our leaf will be sitting like this. Page table entry, right? So which entries we have to configure here? Now we can keep splitting as well, like you say. So we can split, we can shift it by 12 and mask it with, what is this number even? Comes up with 0. If we put 1 here, not surprisingly, it will come up with 1, right? If we put 2 here, come back was 2, and this is 3, right? Agree? So then we configure those entries 1, 0, 1, 2, and 3 to point where. That's kind of interesting. So what will we? Now we have to be concrete because it says, look, we have to put those numbers. Huh?
We already divide the physical memory in 4 pages. So where we can get the address. First one we divide like 0x0. Second will be, I mean, we'll be adding 4 KB place, right?
Right. But when you add a 4 KB but a physical page number, so this entry needs to have 1, this entry needs to have 2, this entry needs to have 3, right? If I suddenly say, look, instead of like mapping from 0 to 16, because this becomes a little bit confusing because 0, 0, 1, 1, 2, 2, 3, 3, right, a little bit off. So if I say that we map from 4 kilobytes to, what is it, 16 plus 4, to 20 kilobytes, right? How will these entries change? No, then all of them? All right, now I ask you to map those pages, page number 1, page number 2, page number 3, and page number 4, physical pages, right? So I said I dropped 0 because I say this one is not mapped. So the address, which is 2 gigabyte, this address, 0x80000000, which lands us on this entry, will map to physical page number 1, right? So then we will put 1 here, right? What we will put here? 2, 3, and 4, right? And what if I say, like, I mean, at this point, I guess it has to be clear, right? So that's how you construct a page table, right? Good? Any questions about it? 5 more minutes. Any questions? I can switch back and probably we'll have time to cover one more question, but do we have any questions in class? All good. Page tables is probably the most confusing topic. Relocation is the second most confusing topic, right? Everything else we kind of know, right? Okay, which one we were looking at? 2B. So 4A. Okay, let's take a look at 4A. Okay, like we already did this relocation example. So to I don't know, like what was the question? 4A. What is meta defined? Don't get the question, but we'll try to answer on Piazza. Okay, let's quickly take a look at this fall 2021. That's the recent one. 1, 2, 1, 3, 1, 2. You're trying to implement a fork bomb. In other words, the program that forks endlessly until it exhausts the memory of the system, with the code below. You're running on a Diffie machine that has a ton of memory and can support a ton of processes. However, each process is configured with a 4096 byte stack. How many processes you will be able to create? So in this specific question probably falls after the midterm. So I ask questions about how many processes x86 can create. For that, we need to understand the layout of x86 process, which we will understand after the break, and we'll go from there. But roughly speaking, you need to eyeball, like essentially, how many pages will be used when you create a new process. And to answer this question, if you say like, okay, forget about x86, imagine it's some abstract system, right? So you say well, at least fork will say you need a couple of pages to create a page table for the new process, right? So to be honest, like you say, look, even if this is a code section, maybe you don't even have a data section, so this is not present, right? It gets a little bit into the woods because you can say, okay, I can start sharing the code section, stuff like that. So let's not go into that. Let's just quickly take a look at another question, 1.3. Can you change the program above to really exhaust all available memory on the machine by forking endlessly? Good question. And I don't know the answer. Don't know. Although I probably came up with this question. Ah, okay, got it. Man, yeah. That's a good question. I cannot answer it right away. Okay, let's just spend 2 seconds on it. Yeah, I got it. That's why it was worded so weirdly, right? You say, so you're saying, okay, man, like I'm a super duper clever hacker. I want to build a fork bomb. That's why it's underdefined, and actually it falls into before the midterm question. So you say, like, how many times you will be able to fork? So who can tell me? There is a limitation here, right? So
Something about stack size being limited in this question.
correct.
So is that first that 4,086 divided by whatever the overhead for function call is, which is 32.
Depends on whether you maintain the stack frame or not. So if you don't maintain a stack frame, then essentially every time you invoke this function, you will use at least 4 bytes on a stack, right? Right? Just because it's a call instruction. And this call instruction essentially pushes something on a stack, right? And then you say, I'm in my recursive fork. So I recurse into this function, I fork again. So it's a process number 2. And again, you do recursive fork. And you again use 4 bytes here, right? Which means that in the max case, you will be able to fork 1024 times, right? And if you maintain this stack frame, then you will push EBP on a stack. So this number goes by half. So you will have 512 times, right? So it's a good attempt to build a fork bomb, but not ideal because you're using space on a stack, right? So how will you change this to really be a fork bomb?
While true.
What?
While true.
While true fork. Yeah, that will work because this one doesn't use any memory in a stack, and so you will be forking for as long as the operating system supports it. That's the question essentially here. So, okay, good question. On Piazza, I felt proud of myself asking it last time. People were probably like, what the hell? But again, my point is not to essentially tell you, okay, you guys don't know how it works. I don't know how it works either, right? The point is to kind of hint you that you should think about those things in those terms, right? So the program executes some number of times until it runs out of stack space. Okay, thank you. So I'll see you then Thursday.
Why is it 4 bytes? The return address